Hello everyone, Shauna here coming to you this week with your check-in for geometry. This week we're going to start the week by continuing with our discussion of similar triangles, but we're actually going to learn to use some of the properties that you learned about of similar triangles to prove that triangles are similar. So let me show you the set of slides for the first lesson that you'll cover this week. This section, 5.3, has 12 slides, so make sure that you have them all. We had some reports that some people were having trouble with all the slides. We're going to prove that triangles are similar using AA, that's angle, angle, SSS, that's side, 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 and SAS, that's side, angle, side, okay? Remember, we're proving triangles to be similar. So their corresponding parts are proportional. So the first theorem that you get taken through is angle-angle similarity. So you see it in green. If two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar. And she's color-coded this for you. And we have some examples to show you. So if you look here, this is not a proof. You will be writing proofs, but you start with being able to identify the similar triangles and tell why they're similar, which property, whether it's angle, angle, side, 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 or side, angle, side, you're using. So it says, explain why the triangles are similar. Let me make sure that I'm okay. I was just checking my files for a second here. Meanwhile, so we have angle A is congruent to angle D because they're both right angles. And we see that we have a vertical angle, BAC and EDC, right? So we can say that triangle ABC is congruent to triangle DEC by angle, angle, because that angle at C, that vertical angle there, BCA is congruent to DCE by vertical angle. So the triangles are similar to each other because of the fact that angle A and angle C are congruent in both. Let's look at another example here. Using the information given in the following, tell how you know they're similar and find all the missing measurements. Well, you have 17 degrees at the top vertex. You have 17. You have 45 on the bottom left. So two angles of one triangle are congruent to two angles of another. They're similar. And you can find the third angle given the fact that you know that the angles in any triangle add up to 180 degrees. So she gives you the solution here, and you can use similarity to find the missing pieces. Now the next theorem that you're going to learn, or the next part of the proof, is side, side, side. So if three sides of one triangle are proportional to three sides of another, then the two are similar. And similarly, you're going to have examples for that. And finally, in this section, we have side angle side similarity, which the only thing here is you have to be a little bit careful that the angle that you're given is between the two sides that you're given. If two sides of one triangle are proportional to two sides of another triangle and their included angles are congruent, it has to be the included angle, not the angle that's on the other side. That's the only little caveat there. And there's examples of that. So this section is fairly straightforward. I'm going to stop sharing this section at this time and share the other sections that you'll be covering this week. The next section that you'll be covering should be very familiar to you. It's a whole section devoted to the Pythagorean theorem. And if you've taken algebra, if you remember your algebra, you will remember the Pythagorean theorem. You might not remember the name of it, but you will most likely remember this theorem. It only applies to right triangles, and we've talked a little bit about it already, and you already know something about it. But let me show you what's in this section here. This presentation, by the way, has 17 slides in it. So just so you know, it has 17 slides. So the Pythagorean theorem. So here's how we do this. And if an altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and to each other. So this is more extensive information about right triangles and Pythagorean theorem. This is saying if you start with a right triangle and you draw an altitude from the vertex that is the right angle, that includes the right angle to the hypotenuse, you split the triangle that you started with into two smaller triangles, both of which are right triangles, and both of which are similar to each other and to the original. Okay. The next theorem says that the length of the altitude to the hypotenuse, so the length of the altitude that you draw, the perpendicular line that you draw to the hypotenuse, is the geometric mean of the lengths of the segments of the hypotenuse. So you'll learn about the geometric mean in this lesson. I'm not going to go into it here, but essentially there's a relationship between the length of the altitude and the length of the two parts, the two segments that you create when you draw this altitude. So there's a relationship in this picture between the length of CD and the length of AD and AB, AD and DB, okay? You'll learn about that when you study the geometric mean. And then we also have something about the length of each leg of a right triangle. So the legs, remember, those are the ones that are not the hypotenuse. So the shorter sides. The length of each leg is the geometric mean of the length of the hypotenuse and the length of the segment of the hypotenuse adjacent to that leg. So if I want the leg BC, for example, it's the geometric mean of the hypotenuse, which is AB, and the length of the segment of the hypotenuse adjacent to BC, which would be DB. So I'm looking at, to get BC, it's the geometric mean of BD and the entire hypotenuse, AB. And again, she'll go over that with you in the slides and in the book. Then we have the Pythagorean theorem, the converse of the Pythagorean theorem, and then we have something called Pythagorean triple, which might be a little bit new to you. You may have seen these, but certain lengths of triangles form not only triangles, but they form right triangles. They're guaranteed to satisfy this relationship. Leg squared plus leg squared equals hypotenuse squared, or a squared plus b squared equals c squared. And she gives you some of the common Pythagorean triples for that. And there's quite a bit of discussion on Pythagorean triples in the chapter. And there's a chart at the very end. These are not an exhaustive list of Pythagorean triples, but these are some common Pythagorean triples. So if you see the lengths of the sides of a triangle, then you can know that you're dealing with a right triangle. You may memorize a few of these. You do see Pythagorean triples quite a lot in other math classes. So you may want to memorize, especially the 3, 4, 5, the 6, 8, 10, the 5, 12, 13, and the 8, 15, 17. Those are the ones that I've seen the most. But again, not completely necessary, but they do show up again. And we have one more section in this week's lecture, and it does show up quite a lot in higher mathematics. In first and second semester calculus, it shows up quite a lot, and also in trigonometry and pre-calculus, and that is the idea of special right triangles. And we don't necessarily mean here Pythagorean triple, although those certainly qualify as special. But here we're talking more about the idea of, of 30, 60, 90 right triangles, and I'm going to try to bring it up for you if I can right now. There we go. Let me share my screen here. We're talking specifically about 30, 60, 90 right triangles and 45, 45, 90 right triangles. Those have very important properties that we're going to learn about in this section. And so you may have, or you may be able to intuit this a little bit, because we've talked about isosceles triangles that have two sides the same length at least. And in a 45, 45, 90 right triangle, the legs are the same length, which you might expect because the angles opposite them are the same. And if you do a little algebra, you'll find out that the length of the hypotenuse is equal to whatever the length of the leg is times the square root of 2. It just turns out that way, but you can also prove that using the Pythagorean theorem and algebra, which she does for you further in the slides. And then we have the 30, 60, 90 right triangle. And in the 30, 60, 90 right triangle, the side opposite the 30-degree angle is the shortest. The side opposite the 60-degree angle is the medium length, and the side opposite 90 is always the longest. Now, I like to think of this as Goldilocks, the Goldilocks rule. And it comes from the story of Goldilocks and the three bears with, the baby bear had a baby bowl of porridge. The mama bear had a mama-sized bowl, and the dad had a papa-sized bowl. Well, the 30-degree angle is the smallest. That's the baby. He's opposite the shortest side of the triangle. Now, the dad-sized angle, the 90 degrees, the hypotenuse, is always twice as long as the short side. So basically, the dad size eats twice as much as the baby, and mom eats what the baby eats times the square root of 3. That's how that looks. You need to memorize these relationships, not so much the numbers, but the relationships. And you can use these to find different lengths of triangles. And as I said, they have properties of their own, and they also have converses when you turn them around. But that's about all I want to cover right now for your overview for this week. I hope that was helpful to you. As always, if you have any questions, feel free to reach out to us. Feel free to see me during tutoring hours. Feel free to message us, and hope you're doing well. Hope you're staying safe, and I will talk to you very soon. Thank you, everyone. Bye for now.